All right, so first, checking conditions. All right, these are the same three conditions that we had to check when constructing confidence intervals for a population. All right, for a population proportion, sorry. We have our random 10% and large counts conditions. All right, these conditions must be checked before performing a significance test. So before you do calculations, these things must be checked and must be confirmed. If they are not met, your calculations aren't really any good, right? So once again, the conditions are random. Data need to come from well-designed random sample or randomized experiment. 10% when sampling without replacement, check that the sample size is less than 10% of the population. And large cows, both the number of successes n times p naught and the number of failures n times 1 minus p naught are at least 10. Right, successes or failures are determined based on your context. Right, so these are the same three conditions that we've seen previously. Right. Next, we're going to jump to screen 7. The one sample z-test for proportion. This is our inference method that we're using when testing a population proportion. It's the one sample z-test for proportion. Right. We're going to choose an SRS of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis h naught such that p equals p naught, we compute the z statistic. Right, so to test our null hypothesis, we must find a z statistic, very similar to a z-score. We'll use it in a very similar way. Z equals p hat minus p divided by the square root of p naught times 1 minus p naught divided by n. All right. This is our z statistic. We're going to find the p-value based on this z statistic by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis h sub a. Right. If our alternative is that the true proportion is greater than the null hypothesis, right, we're looking at the area under the curve greater than z. If we're checking to see if the alternative is that p is less than p naught, again, area under the curve less than z. For a two-sided alternative, we will check the z-score for the positive side and the negative side. Essentially, we'll use symmetry and find the area under the curve for one of these and just double it, either the left-hand side or the right-hand side. Okay, and that is how we can do that. So again, we'll need the check conditions. We'll need the one sample z-test for a proportion. And on screen 11, our 4-step process. This is a very important process. This allows us to make sure that we're covering all the bases, right? That we're showing and doing everything we need to do when answering questions about testing hypotheses to get as much credit as possible in a testing situation. All right. So, and again, the 4-step process is ideal for organizing our work and helps make sure we don't skip anything that we need to do. All right, so we have the 4-step process for significance tests. This applies to proportions and means. We'll use the same 4-step process. We just change the inference method depending on if we're doing proportions or means. So step 1, we need to state, what are we going to do? All right, what hypotheses do you want to test and at what significance level? Define any parameters you use. Plan. Choose the appropriate inference method. Check conditions. In this case, dealing with proportions, we only have the one inference method available right now. It's the one sample z-test for population proportion. Do, if the conditions are met. So part of planning is checking our conditions again. do. If the conditions are met, perform calculations, compute the test statistic, right, essentially the z-score, and find the p-value. Use table A to find the proportion or the area under the curve based on the test statistic. Conclude, make a decision about the hypotheses in the context of the problem. This is incredibly important. Your conclusion must refer back to the context. It is not enough to simply say, we reject the null hypothesis, we have evidence for the alternative. While it might be correct, it is not sufficient. You have not actually answered what's been asked. You need to tie it back in with the context. Tell me what that means in the context of the problem. All right, so again, this is our 4-step process. Is there anything I can clarify before we move on? All right. So that brings us to slide 12. Side effects, practice with the 4-step process. All right. So this question, you should go through the 4-step process. All right. State, plan, do, conclude. A drug manufacturer claims that less than 10% of patients who take its new drug for treating Alzheimer's disease will experience nausea. To test this claim, researchers conduct an experiment. They give the new drug to a random sample of 300 out of 5,000 Alzheimer's patients whose families have given informed consent for the patients to participate in the study. In all, 25 of the subjects experienced nausea. Use the data to perform a test of the drug manufacturer's claim at the alpha equaling 0.05 significance level. I do have a link here to the formula sheets and tables, so if you need table A, you can click this link. All right. And again, I recommend doing your work on paper and then uploading a picture of your work using the upload image option in the bottom left corner of the text entry box. You could also just simply type into the text entry box. In our next Desmos activity, I have more options available for submitting answers, but we'll talk about those when we get there. Okay. We're gonna talk about this. I know that many of you guys were working through this. I saw some really good starts here. You guys are showing work, showing ideas, so I appreciate that. I'm gonna recommend that you go to the shared screen if you're on your own, like Desmos tab here, because I'm gonna walk us all through the 4-step process on solving this question. So here we go. All right, so the 4-step process on our side effects question. The first thing that I did, which is something that I do for my own process, it is not part of the 4-step process, is this top little section here, right? This is just basically listing my data and variables. It is not part of the 4-step process. It is just so that I can access that information easier, because I'll need to use it while I do the 4-step process. I don't want to have to go back into the context again to find these numbers each time I need them. So I'm going to write them all down in a way that I can use them. Right, we have our null hypothesis, H naught. We have our alternative, H sub A. Right, the sample size, N, equaling 300. We actually know the population size that we're sampling from. It was given in our context, so I have that written down. That's 5,000. The sample proportion, P hat, 25 out of 300. Is approximately 0.083. You could add more decimal places to this. It's just a repeating 3 at the end. It's 0.083333333333 forever. So you could keep a couple more of those 3s if you like and be a little more precise. I chose to round to 3 decimal places here. And lastly, we have alpha, which is our significance level, and we were told to use 0.05, which is fairly common. All right, so this is just all the data that I can get from the context. These are the numbers and the variables that I'm going to use. So then that gets us to step 1, right? Stating what we're going to do. All right, we want to perform a significance test on the hypotheses H naught such that P equals 0.1 versus the alternative hypothesis H sub A such that P is less than 0.1. Right, where P is the true proportion of the 5,000 Alzheimer's patients. That is our population. It's not out of all Alzheimer's patients, it's just the 5,000 in this study, or that could be considered for the study. Who would experience nausea while taking the drug at an alpha equaling 0.05 significance level? All right, so that's what we're going to do. We have in our statement, we are saying what our hypotheses are, what's the parameter we're using, P, and what it represents, and the significance level. Okay, so then we can move on to the plan step. Right, and there's a couple of important things in our plan step here. We have the statement, if conditions are met. It's kind of just like the intro part of our statement here. They're saying, like, if things work out, we'll do this inference method, right? And in this case, we're using the one sample z-test for the population proportion P. The one sample z-test is the inference method. All right, this one sample z-test allows us to like maneuver with the numbers in such a way that we can now hopefully make an inference about the entire population based on this data. Right, and then we check our conditions random. A sample was chosen randomly. We were told that in the context, so we're good here. Right, the 10% condition, 300 out of 5,000 is equal to 0.06, which is less than 0.1. So we're less than 10% of the population we're sampling from, so we're good. And large counts, 0.1 times 300 is 30, which is greater than or equal to 10. And 0.9 times 300 is equal to 270, which is also greater than or equal to 10. We're good here because both possible number of successes and number of failures are both greater than or equal to 10. Right? All 3 of our conditions are met, so we're free to continue. And we move to the do phase. In this phase, remember there's 2 things that we're doing, right? We're finding our test statistic, right, which in this case is Z, and we're finding the p-value based on our test statistic. Okay, so then Z is equal to p hat minus p divided by the square root of p naught times 1 minus p naught divided by n, which, using the values we have listed up at the top, we have 0.083 minus 0.1 divided by the square root of 0.1 times 0.90 divided by 300. It is very important to realize that all of this fraction, the 0.1 times 0.9 divided by 300, is under the square root sign. Okay, we're taking the square root of that whole thing. Right, so you can add the parentheses for emphasis if you like. If you're putting this in your calculator, you should put parentheses around that division to make sure that your calculator knows you're taking the square root of this whole thing. Otherwise, you might get an error. Well, you'll get an answer, but it'll just be the wrong value. All right, so then we end up with negative 0.98. Right, this is essentially akin to the z-score that we're now going to find on table A. Right, based on the original context, we're looking for the alternative claim is that the proportion is less than 0.1. So we're going to look on table A for the probability that Z is less than 0.98, negative 0.98. right? And using table A, right, we get 0.1635. Okay. And then lastly, we just as kind of like a wrap up to our do part, this is not a conclusion. Right? We have the p-value is greater than 0.05, which then means that we fail to reject the null hypothesis. This that I have written here is not a conclusion. It is just something that's there so that I know where I ended in my calculations. My calculations showed that I'm going to fail to reject the null hypothesis. I do not have convincing evidence for the alternative. Well, so then we actually write the conclusion, right? Because the p-value 0.1635 is greater than alpha equaling 0.05, we fail to reject the null hypothesis. We do not have convincing evidence that the proportion of these 5,000 Alzheimer's patients who would experience nausea while taking the new drug will be less than 10%. Right? We have to tie that into the context, right? We did not just say we do not have convincing evidence that the alternative is true, right? That doesn't give me any connection back to the original context. What does this all mean? If I fail to reject the null hypothesis, that second part of the conclusion tells me what that means in the context. Okay. Is there anything I can clarify? Are there any questions? Okay. Alrighty. Oh, wait, one last part. I forgot. Leave that there. We can also use our calculator. All right. So the other thing we can do to get our z statistic and our p-value is use the calculator, right? So if we go to stat, it's kind of in the top middle here, right under delete, and go over to tests. Far right, we'll click over twice to the right, we'll get on tests. We want to do the one proportion z test. It's the fifth option down. I've already entered in the data for this. All right, our null hypothesis for p is 0.1. Right, x is essentially the number of successes. In this case, the number of people who got nauseous. Right, which we were told it was 25 out of 300, right? So this is x equals 20, x is 25, n is 300, our sample size. And the alternative is that we are less than the null hypothesis. Right, and so we can change what this is. So we could say it's not equal to the null, less than, or greater than. Right, and we would just click enter on the one that we want. We want less than, so we'll hit enter. And then we will calculate. Right, and it very quickly finds that the z statistic is negative 0.96225044486, and that gives us a p-value of 0.16796, blah, 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 and our sample proportion is 0.08333333, which we already found. All right, so this is another strategy, right? Slightly more time effective for finding the z statistic and the p-value. I would suggest learning and knowing how to do both and being able to do both on each type of problem so that you can have confidence in the work that you're doing by hand as well. The numbers will not always match up. Notice I have negative 0.98 and they have negative 0.96. That's due to rounding, and that's okay, right? We also got, I got a p-value of 0.1635, and they got 0.1679, right? Slightly different, close enough, right? There's not enough error here for me to get a different result, a different conclusion. So it's not concerning, right? When you do stuff by hand, there will be a certain amount of rounding error that will cause what you did by hand to be different than what the calculator finds. Okay, and that's okay. Is there any questions? Anything I can clarify? All right, we'll move on. Type 2 error and power of a test. All right, a significance test makes a type 2 error when it fails to reject a null hypothesis that really is false. Right, so essentially a type 2 error is you should have found evidence that the alternative is true, but you didn't, and you failed to reject the null hypothesis. Right? There are many values of the parameter that make the alternative hypothesis true, so we concentrate on one value. The probability of making a type 2 error depends on several factors, including the actual value of the parameter, which we don't always know. We usually don't. A high probability of type 2 error for a specific alternative parameter value means that the test is not sensitive enough to usually detect that alternative. Okay, so if we have a high probability of type 2 error, our test, we might need to rethink how we're running our test and how we're collecting our data and those types of things, our samples and all that stuff, right? Because a high probability of type 2 means that we're not very likely to find the result that we're actually interested in finding. Right? The power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level alpha when the specified alternative value of the parameter is true. So the power of the test is essentially the probability that you will find convincing evidence for the alternative when the alternative really is true. All right. And we like having the power should be higher if possible to give us, you know, a test that is sensitive enough. Right. And to help this make more sense than my own ramblings, we have a short video from AP Daily that I thought helped explain this a little bit better than I can. Oh, there we go. Cool. Hopefully you can hear it. Let me know if you can hear it. I should have it set up properly. We'll see.
Choice in significance level. Now let's talk about power and type 2 errors. In many contexts, a type 2 error is more consequential. I say this because in most research, researchers are trying to show that the alternative is true. And if they make a type 2 error, that means they didn't find convincing evidence the alternative is true, when it really is. So their suspicions were correct, they just didn't get the data to back up their suspicions. So for a researcher, a type 2 error is really bad news. Well, they came up with a word to talk about the probability of avoiding a type 2 error, and that word is power. So power is the probability of avoiding a type 2 error. The power of a test, then, is the probability that a test will correctly reject a false null hypothesis. Notice it says correctly there. Power is describes a correct decision. So the null hypothesis is false, and our data suggests that it's false, gives us convincing evidence that it's false. So power is the probability that we find convincing evidence for the alternative when the alternative really is true. That means the probability of a type 2 error is 1 minus the power. Remember, if power is the probability we avoid a type 2 error, then 1 minus the power is the probability of a type 2 error. Now let's look at an example to put this in context. To investigate if high school students associate the color green with being more natural, 2 student researchers randomly selected 30 students from their school. Each student was asked to taste 2 cups of lemonade in random order and state which one tasted more natural. One of the cups was green and the other cup was white. And unknown to the taste testers, was the fact that both cups contained the same brand of lemonade. From previous videos, remember that we talked about the null hypothesis being p equals 0.5 and the alternative p greater than 0.5, where p is the proportion of all students at this school who would choose the green cup. Now, suppose that researchers used a significance level of 0.05 and that the power of the test against an alternative of p equals 0.64 is 0.45. Interpret the power in context, then find the probability of a type 1 and a type 2 error. So before we answer these questions, I want to reread the question because that first sentence might sound a little confusing. It says, suppose that the researchers used a significance level of 0.05. Well, that's pretty standard. And that the power of the test against an alternative of p equals 0.64 is 0.45. So we're saying the power is 0.45, and it's that number for the specific case that the truth is 0.64. We're not going to get into the calculations in this video, but the calculation of power depends on what the true value is, if it's something different than the null. So in this case, we're assuming the true value is 0.64, and then we've done calculations to show that the power equals to 0.45. Again, you don't need to worry about where those numbers come from. I just want to make sure you understand what it's describing. So interpret the power in context, and then we'll find the probability of a type 1 and a type 2 error. So here's what the power means. If the true proportion of students who would choose the green cup is 0.64, then there's a 0.45 probability that we find convincing evidence that more than 50% of students would choose the green cup. In other words, there's a 45% chance that we'd find convincing evidence for the alternative hypothesis. Now, as far as the probabilities, the probability of a type 1 error is equal to the significance level. That's easy, 0.05. And the probability of a type 2 error is 1 minus the power. So remember, power is 0.45, and so the probability of a type 2 error is 1 minus 0.45, or 0.55.
All right, so hopefully that helped a little bit, kind of clarify what the idea of type 2 error and power are and how they're related. Again, kind of like they mentioned, you're not going to be expected to be able to calculate a type 2 error and power, but you should be able to use one to find the other if you're provided one of them, and you need to be able to interpret what it means. So now, type 2 error and the power of a test. The significance level of a test is the probability of reaching the wrong conclusion when the null hypothesis is true. Type 1 error. Right. The power of a test to detect a specific alternative is the probability of reaching the right conclusion when that alternative is true. That is the power. We can just as easily describe the test by giving the probability of making a type 2 error, sometimes called beta. That's this kind of funny looking B here. It's the Greek letter beta. All right, power and type 2 error. The power of a test against any alternative is 1 minus the probability of a type 2 error for the alternative. That is, power equals 1 minus beta. Also, right, the power, or the type 2 error, is 1 minus power. Right, they're kind of complements of each other. Right. Then sometimes we want to increase the power of a significance test, right? Because that gives us a higher probability of correctly rejecting the null hypothesis because the alternative is true, right? It gives us a better chance of finding good evidence. Right, we can increase the power of a significance test by increasing the sample size. Right, larger samples tend to give us more accurate data. Right, increasing the significance level. Right, so with a higher alpha, right, that should increase the power. We can also increase the difference between the null and alternative parameter values that is important to detect. This difference you usually have little to no control over because it's not your experiment, right? The situations and experiments that we're being provided information for, that we're using in these problems, we can't really change what the parameters are. So we can't really use this one very often. So we usually will be able to increase sample size or increase significance level. All right. So that leads us to the last problem here. All right, and this is using the same context on screen 12 with our Alzheimer's medication. All right, part A, describe a type 1 error and a type 2 error in this setting. Don't just tell me what a type 1 error and a type 2 error are. Tell me what they would be in this context and explain the consequences of each. B, the test has a power of 0.54 to detect that P equals 0.07. Explain what this means. And last, part C, identify 2 ways to increase the power in part B. Okay, I'm going to assume that this was a little confusing because I don't see any responses for this question. Hopefully that doesn't mean that my system's not cooperating, but well, let's talk about this one. All right, so again, I suggest going to the shared screen here so you can see the OneNote page here that I have, and we'll talk about this. So first, part A, what is a type 1 and type 2 error in this setting, and what is the possible consequence of each? Right, a type 1 error in this context would be finding convincing evidence that less than 10% of patients would suffer nausea after using the drug, when in reality at least 10% would. Right, a consequence is the new drug is used on more patients, leading to excessive nausea. Right, type 2 error would be failing to find convincing evidence that less than 10% would suffer from nausea, when in reality less than 10% would. Consequence, the new drug is used less, even though it rarely causes nausea. Right. So again, we're not saying what the type 1 or type 2 error is, like definition-wise. We're saying what it would be in the context. Is there anything I can clarify about part A? Part B, if the true proportion of Alzheimer's patients who would experience nausea is really 0.07, there is a 0.54 probability that the result of the study would provide convincing evidence the true proportion is less than 0.1. So again, the power is the probability of finding convincing evidence of the alternative given like the actual parameter value being something. Like in this case, we have P equaling 0.07. So if that's the true proportion, then our test has a 54% probability of finding convincing evidence. And part C, the 2 ways we can increase the power is increase the sample size or increase the significance level. In this case, we cannot change the difference between the parameters. All right. Is there anything I can clarify about this last question? Parts A, B, or C? All right. So lastly, that is the end of this Desmos activity. Real quick, while I'm sharing my screen, we're going to look at the course. Please, guys, remember there are a lot of resources in the modules for all the chapters. Specifically, pretty much everything for chapter 9 is ready. We have all the notes and resources for 9.1, 9.2, 9.3, all the practice problems and solutions for the 3 sections. Plus the activities are linked in here, and the assessments are also available now. You don't need to do them right now. You could start them if you like, but they are available. Keep in mind we will be doing, or at least starting, section 9.3 tomorrow. We'll see what we can get through tomorrow, and then you should have all the base knowledge to be able to start the assessments. But please, I do highly recommend looking at the notes and resources for each section. You don't need to write a bunch of stuff down about it, but you should at least look it over and see if there's anything useful to you. There's a study guide in there. There's the PowerPoint presentations. There's videos showing examples. All right, lots of resources. Please don't forget that these things. Grading period ends on the 16th, I believe. Yeah. Friday, April 16th is the last day of the second grading period. Okay. All right, but again, please make sure you have all these resources. Use them as much or as little as you like. Now, I'll stop sharing my screen. That is the lesson for today. If there's any way that I can help you, support you with stuff from this lesson, previous lessons, previous assessments, please let me know. I'm happy to help. Otherwise, I hope you guys have a great rest of your day, and I will see you all tomorrow.